All right, guys, so make sure that you have your notes out and you're ready to take notes as you go through this, and then we'll do some more examples tomorrow in class. Okay, so yesterday we learned about, or earlier today, we learned about lines and segments and rays, okay? Now we're going to talk about angles. Okay, so the basic idea here for angles, an angle, and you can pause if you need to, an angle is a figure formed by two rays, so let's draw two rays, and the two rays come from the same endpoint. So there's one ray, and here's my second ray that comes from that same endpoint. So they have to share the endpoint. So those are, we call these the sides, and we call this common endpoint right here the vertex, okay? So an angle needs at least 3 points then, because it needs the 2 points on that ray and then that extra point here. So let's call this angle MBC. Okay, so here we've got an angle. I'm going to get rid of these guys so you can see it a little bit better. So let's start off by labeling our two sides of our angle. So the sides of my angle would be the two rays, and they have to be labeled as rays. So MB would be the one side, and MC would be my other side. So those are my two sides. What's the vertex of this angle? That should be the common endpoint, M. Okay, so that's our general definition for an angle, and then we're going to talk about different types of angles, okay? All right. Before we do that, let's talk about how to name our angles. So, okay, I'm going to go back to the one that I just had, M, B, C. So first of all, we use an angle symbol. So literally it's like a little mini angle. And then I use the three letters that create my angle. And it's important what order they go in. It has to go, your vertex has to be in the middle. And then you have 1 point on each side. So BMC would be one angle, one way to write that angle. Now you could also go in the reverse order. So you could also say angle CM. Those are the same exact angle. Okay, so again, it kind of helps if I'm naming an angle, I should be starting on one side and then going to the vertex and then coming back out. So like if I name it BMC, then you know I'm talking about that angle here. So you're kind of creating the mouth of the angle. Okay, so one way is using the vertex in the middle and then a point on either ray. Okay, that's one way to name an angle. You can also name an angle using a number in the mouth of the angle. So sometimes we'll put numbers in here and we'll call this angle 2. Okay? All right, and then the last version only works if you only have two rays coming from your angle. And if so, you can call this just by the vertex, angle M. Here's the problem though. If I have a drawing where I have all sorts of rays coming from a common endpoint, then I can't just call this angle M, because if I call it angle M, it's ambiguous. Do I mean that angle? Do I mean this angle? Do I mean the whole thing? So we can't do that. So you can only call it by the vertex if you only have two rays coming from that vertex, okay? All right, so down here, since I already have this drawing, let's label some angles in this drawing. So like I'm going to call this angle 3, I'll call that angle 4. So if I wanted to talk about angle 3, I could also call that, let's see, well, angle 3's vertex is point M, so that would be in the middle. And then I need the points on each side, so like TMQ would make that angle. Or you could have called it QMT. If I want to write angle 4, I would need this angle. So I could call it Q to M to R, angle QMR. Okay, and then if I wanted to talk about the whole big angle, then I would do T to the vertex to that R. So the big angle is angle TMR. Okay, so that's how we label angles. What about types of angles? Now this you guys should already know. Acute angles, they're usually measured by how many degrees they open, right? The angle. So you can kind of think of it like if this is my little angle and then my angle opens to a particular amount of degrees, right? Okay, so a lot of you already know these. Acute is when your angle is bigger than 0 but less than 90. So see, these are parentheses, so they have to be bigger than 0 but less than 90. So Most people are familiar with acute angles. They're less than 90 degrees. A 90-degree angle, most of you are already familiar that that's a right angle. And the way that we show in a figure that that's a right angle is we put a little box in the corner. And then that lets our reader know that that's perfectly 90. Obtuse is bigger than 90 but less than 180. So most of you are comfortable seeing something like this. So maybe that angle is like 120 degrees. That would be something that's obtuse. Maybe this one's 21 degrees or something, okay? And then last but not least, a straight angle is an angle that goes all the way 180 degrees, which would basically mean you have two opposite rays, and so it opens and creates a straight line. So that's why we call it a straight angle. So a straight angle is perfectly 100 degrees, and it does form a line, okay? Okay, so acute, right, obtuse, and straight. So make sure that you have those down. If you need to pause it, go ahead, because I will ask you to classify these. Okay. So you know how yesterday, or earlier today, we did segment addition postulate, where I said you can add up the parts of a segment. So like if I had MTV, you could say, well, if I add MT, this part, plus this part of the segment, that should add up to the whole segment, which would be MV. That was segment addition postulate. Basically, add the parts up and set them equal to the whole thing. Well, that's true for segments. It's also true for angles. So if you have angles like here, let me show you what I mean by this. If I have two angles that are next to each other, I'm going to define this in a minute. It's called adjacent. Then I can add those two angles to get the entire thing. So I need some letters. So let's call this Q, P, S. So if I wanted to add angle 1 and angle 2, I would get angle QPS. Now I will tell you this. You know how earlier I said when we talk about a segment versus just its length, right? So this is the actual segment figure. This is the length. When we want to talk about measures for angles, we put a little m in front of the angle. So this means measure of angle 1. Okay, so I'm going to take the measure of angle 1 and I'm going to add to that the measure of angle 2. And all together that would add up to the big angle, and the big angle is QPS. Okay, so I could add up 1 and 2. So maybe, for example, if I told you this was 30 and this was 50, then you could say, well, then that means the big angle must be equal to 80. So a lot like what we did yesterday, and they get a little bit trickier, but that's the general idea. So you can add up, one more time, angle addition postulates basically say, again, you can add the parts and set it equal to the whole thing. Okay. So again here, so if I was right, so this is the specific angle addition postulate. So if I have a big angle AOC, so A would be out here, O would be the vertex, C would be on the other ray. If there is a point B and it's somewhere inside my angle, so it could be maybe here. If I were to draw this ray, then if I add A, the measure of AOB, here's AOB, this angle, that one right there, with BOC, that angle. We use arcs to kind of, delineate between different angles. If I added those two, I should get the huge big angle, which is all of that, right? Okay. So we can only use angle addition when we have adjacent angles. So these are adjacent is like if I said my house is adjacent to yours, you might think of that as like next to, which isn't bad, but we need a little bit more to describe adjacent. So to be adjacent, three things have to happen. You have to have a common vertex, you have to have a common side, but no shared interior points. So let's look at what I mean by that. So up here, these two angles, AOB and BOC, are adjacent. They have a common vertex. They both have the vertex O. They have a common side. They share this side. And they don't overlap. That's really what the common interior is. They don't overlap with each other at all. So those are considered adjacent angles. So let me give you some examples of non-adjacent angles. Well, yeah, that's adjacent angles next to each other. So non-adjacent angles could be like this. Like in this example, if I talked about angles 4 and 5, They have a common vertex. They do. They both share that point. They don't overlap, but they wouldn't have a common side. So 4 and 5 would not be considered adjacent to each other, which I think most of you would agree they're not adjacent. Okay. In this picture, let's compare angle. We'll compare angle MTQ, which is the big angle, and angle 1. So do they have a common vertex? Yes. Do they have a common side? Well, angle 1 has side TQ, and so does the big angle. So technically, yeah, they both have that side. But would you say the big angle and 1 are adjacent? No, because they overlap. Like angle 1 is inside of angle MTQ. So the big angle, MTQ, and angle 1 are not adjacent. So again, I'm giving you examples of non-adjacent. And then the last one could maybe be something that looks like this. And I'll call this angle 1 and angle 2. So these two are not considered adjacent because even though they share a side, kind of, right? They kind of both share that side. They don't overlap, but they have two different vertices. They have two different, they each have their own vertex. So those aren't considered adjacent. So adjacent, most of you I think are pretty comfortable identifying adjacent angles, but they really do need to be right next to each other. They need to have that common shared side in the middle, and they need to have that same vertex. So you can only do angle addition if you have adjacent angles. We've already talked about congruent versus equal. So just like you can bisect a segment and cut a segment into two guys, you can bisect an angle. So an angle is just a ray that divides an angle into two congruent adjacent angles. Okay, so take a look at this. Let's say that I gave you my big angle, A, B, C, and if I want to bisect the angle, I would have to have a ray. So my ray needs one more point, so I'll call this D. It would have to have a ray, oops, such that this ray has to divide the big angle into two equal parts. Now the way that we show equal is by using similar arcs. So see how they both have an arc? That means that they're equal. Or if you have more than one diagram, you can put two arcs on this one and two arcs on that one. So see, that's kind of showing that those two things are equal. We can't use dashes because there's no way to use a dash, so we use an arc. And I don't know if you noticed this, but see how I kind of spaced them apart? Like if I didn't do that and I put them right next to each other, you might not know if I mean that these two are equal or if I'm just talking about the huge big thing. So that's why when we do our arcs, we like to space them out like this. So that would show that those two things are equal to each other. So I would know that BD, ray BD, bisects the big angle. What's the name of the big angle? I'm going to call it angle ABC, but you could also call it CBA. Remember, the vertex has to be in the middle. Okay. So at this point, you would do some work with that. I'm just going to show you a couple practice ones so you can see how this might look. So, okay. In this example, I could tell you, so if I tell you that the measure of angle MQZ, which is angle 1, is equal to x plus 10, and the measure of angle 2, I'll make that one easier, is 4x plus 5, and the measure of the big angle, MQP, is, let's say, 100. Okay? And I want to find x. Okay. Well, the first thing that I would do is label my shape. So they didn't say it was a bisector, so I don't know 1 and 2 are congruent, so I'm going to label what I do know. Angle 1 is x plus 10, so this part is x plus 10. Angle 2 is 4x plus 5, so that guy's at 4x plus 5. And then the whole thing, MQP, all of that opening, is 100 degrees. So what can I do here? Well, since these are adjacent, I can add them together to get 100, angle addition postulate. So I'm going to say measure of angle 1 plus measure of angle 2 equals the whole big thing, which is MQP. So here's my symbol form. Now I'm going to fill in my information. Angle 1 was x plus 10. Angle 2, I'm going to add the other angle, 4x plus 5, and that should add up to the whole big thing, which was 100. Then I would just solve like normal. Let's subtract 15, and I would divide by 5. And so for this one, I end up with, let's see, what do we get here? 17. And then remember, if I wanted to get the actual measure of angle 1, I could just plug 17 back in. So instead of x plus 10, I'd have 17 plus 10, so 27. And I could do the same thing for angle 2. Measure of angle 2 would be 4 times 17 plus 5. And so in that case, I get 73. Now that you know this is 27 and this is 73, do you think that this ray bisected the big angle? So this one's 27, this one's 73? No, they would have to be equal on either side if it was a bisector. So that's some of the stuff that you can do. The other thing that you might see for this section is if they do tell you it's a bisector, then you can say, oh, I know the two parts are next to each other are equal. So for example, if I gave you a drawing and I said, that BT bisects angle KEE, then you could label some stuff. Let's take a look at that. So BT, this guy, bisects the big angle. That means this angle and its next door neighbor, the adjacent angle, are congruent. So if they gave you information like, oh, this is 2x plus 11, and oh, this is x, plus 50. If these two things were equal, this is like the midpoint stuff we did yesterday. If these two things were equal, then you could set them equal. You wouldn't have to use angle addition postulate because you'd know that these two things should be the same as each other. So there's a lot of different stuff that you can do. So basically, I guess when we're going to be working with these, we're going to be deciding whether or not we think we should add them up or set the two angles equal to each other. So we'll do more with that in class. Those are the basic angles. Make sure that you know how to label angles and that you can talk about bisectors. Okay. So the intro to the second part. Again, I'm going to go through this a little quick and then we'll do more with it tomorrow. So we're going to learn about postulates and theorems. We've done most of these, but I'll just go through them with you today and then we'll talk more about them in class. So remember this, a line has to have at least 2 points. We talked about that. A plane has to have at least 3 points and they have to be not in one line. So that's the same as non-collinear. Okay, and then space contains at least 4 points and they're non-coplanar. We did this yesterday, but these are just some postulates. Postulates, by the way, postulates are ideas that are accepted as being true. For example, like if I say the word blue, everyone has accepted in the English language that blue means this color. So a postulate is something you don't have to prove. It's just a generalized something that we accept in general. Okay, so these are postulates. Through any 2 points, there is exactly one line. So if I give you 2 points, you can only draw one line that goes between them. If I give you 3 points, then there's at least one plane that would contain all 3 points. And if they're non-collinear, then there's only one. We'll talk more about those. So you need to write these down in your notes. So today, you should be writing these down. If you have 2 points in a plane, so if I have 2 points in a plane, so here's my plane, I'm going to put 2 points on that surface. Then if I connect them with a line, then the whole line is also in that plane, right? So if you draw the line that connects them, it has to be in the plane. And you guys already know this. If 2 planes intersect, right, like the corner of a room, then their intersection is a line. So make sure that you get these guys down. Okay, then we have some theorems that relate these as well. If 2 lines intersect, then they intersect at exactly 1 point. Again, most of you are fine with that. And if there is a line and a point not on the line, so if you have a line and a point not on it, so if I put a point not on it, then there's one plane that contains them. This one I'll get a little bit more into tomorrow, but there's only one plane with that, but we'll talk about this. And if two lines intersect, so if I have two intersecting lines, there's also only one plane that can contain them. So again, I'll go into this tomorrow. So again, what I want you to do is read through these ideas, and I want you to already have them in your notes so that we can go through them and I can do some examples tomorrow. Okay, this is a super simple thing. These are just properties from algebra. Everybody should know these. Addition property. Addition property basically says that as long as you add, if you have two things that are equal, so like if I have two numbers that are equal, a plus b, if I add 7 to this side and 7 to this side, it will still be equal. That's all that addition property says. If I add the same thing to both sides, they're still equal. Same thing for subtraction property. So if you start with two things that are equal, like a lot of times you guys will see this like this. If I said x plus 10 equals 20, you guys do subtraction property to solve. Because you go, oh, I can just subtract 10 from each side and then I get my final answer. That's subtraction property. If you subtract the same thing from both sides, it's still equal. Multiplication property is just like what it sounds like. We use multiplication property to solve when we have like division. So if I multiply this side by 10 and this side by 10, these two things are still equal, and I get x equals 80. The way that it looks, though, is if you start off with a equal to b, then if I multiply this side by c, it's still equal as long as I multiply that side by c. So this is how we see it when we solve. This is what it looks like in a statement. So again, if you're trying to identify what property it is, it's easiest to look at what happens. We started with this, and then we added two equal things to both sides. Or here, I started with a equals b, and then I subtracted something from both sides. Started with a equals b, I multiplied by the same thing. And last but not least, I started with a and b, and I divided the same thing on both sides. So it's pretty easy to see. These are called properties of equality. So when you use them later, you're going to call them like the addition. I do shorthand, and you guys can too, POE for property of equality. Or you can even do this, addition, POE. I'm fine with that. Or subtraction, POE. Or multiplication, POE for property of equality. But you do need the property of equality. Okay. Then we have substitution property. Substitution is pretty easy. Most of you guys use this. For example, you use it like this. If I know x is 7, and I know that y equals 2x plus 3, most of you are very comfortable going, okay, well, I could substitute this in. Instead of x, I can make that a 7, and I can get y. 14 plus 3, so y is 17. That's substitution. Substitution is literally when you substitute something in for another equation. That's substitution property, and it is technically should be written as substitution property of equality. Okay, transitive property is kind of similar, but not quite. Transitive property is kind of like a chain. So you're going to say, if I know A gives me B, and B gives me C, then I can go all the way from A to C. It's kind of like a big chain. So I could show it to you kind of like this. I could say, if the measure of angle 1 is 50, and the measure of angle 1 is the same as the measure of angle 2, then check it out. That means I could kind of chain these all together. So if 50 is angle 1 and angle 1 is angle 2, we can go from 50 all the way to 2. So 50 equals the measure of angle 2. Kind of like that. So it's kind of like you're chaining a bunch of stuff together, right? I always say transitive property, we start with 2, and then we hook them together, almost like a train. You're kind of like putting them together, right? So in this first one, it's kind of like I have equals measure of angle 1, and then measure of angle 1 equals measure of angle 2, and so I can go all the way from the beginning to the end. That's transitive. Reflexive and symmetric are, you're going to have to memorize these. Reflexive, it might seem obvious. Reflexive literally just says A equals A. And we're going to use those later when we start dealing with shapes where we overlap. So like if I have two triangles, for example, and maybe those two triangles share a side, like that side right there, and maybe that side has a side length of 4, I can say these two sides are equal, like this side and this triangle is the same as that because they're actually the same side. So the reflexive property literally just says it equals itself. It's kind of like reflection, right? You see itself. Symmetric is, you guys use this all the time. This is if A equals B, then B equals A. So basically you can flip the equation, right? So you guys use this because you'll have something where you have like maybe 4 equals, or let's do 40 equals 2x. And you guys will say, you know, x equals 20, or sometimes you'll flip it in your brain and you'll say 20 equals x, or I'm sorry, x equals 20. So you guys do this already, where even though the x is on this side, at the end you end up saying it like this. That is technically the symmetric property. Basically, I can move this side over here and this side over here and it's still equal. So symmetric is just, if it's true forwards, then I can flip it and it's true backwards. Okay, the only other property that you might find is distributive property, but most of you will be familiar with that, so we can try that later. And you'll see some of these. These are some of the ones that we're going to do together. And then we'll start doing some proofs in class. And I think, yeah. Again, we're going to start doing a little bit more with proving theorems. Again, a postulate is a statement that's accepted without having to be proved. So those are like our properties. A definition tells us that it's true because that's how we defined it. So like if we define what it means to be a midpoint, that's a definition. And then we have a theorem. And a theorem is something that we can actually prove. So it's going to be important that you label postulates, definitions, and theorems correctly. Okay. So like we have midpoint theorem. Okay, so the midpoint theorem is different than the definition of a midpoint. So let me go back to definition. If you remember from yesterday, definition of midpoint, if this was my picture, right? Okay, so this, for some reason this got cut off. There we go. So if they gave me that M was the midpoint, by the definition, if M is the midpoint of AB, then we would know that the 2 parts on either side were equal. That's the definition. The definition says if you know it's a midpoint, then you know the 2 parts are equal. The theorem is different. The theorem is what a lot of you were trying to say yesterday. The theorem says if you know it's the midpoint, that's the starting part. If you know it's the midpoint, then you know that this distance, A to the midpoint, is half of the whole thing. So like, see this little guy here, which most of you know that. Like if I gave you this was 20, most of you know that's 10 if that's the midpoint. So the midpoint theorem tells us that this little guy is half of the whole thing, right? Or vice versa for the other side. Or that 2 of these little guys make up the whole thing. So that's the midpoint theorem. Definition says the 2 parts on either side are equal. Theorem says that this guy is half of the whole thing. Okay, so that's the difference between definition versus midpoint theorem. Same thing goes for an angle bisector. The definition of an angle bisector is this part. It starts off the same. It starts off if ray bx, I don't know why these all got moved. Sorry, guys. There we go. So the definition says if ray bx bisects angle ABC. So that's the beginning. If it bisects it, the definition would say that the 2 parts on either side are equal. So the definition would say, oh, well then angle ABX, which is this angle, is congruent to angle XBC, the other side. The definition says the 2 parts are on either side are equal, just like definition of a midpoint. The theorem for angle bisectors say that this little part, ABX, is half of the whole thing, right? So this little guy is half. That's what the theorem says. Okay, so difference, you got to know the difference between theorem and midpoint. Or I'm sorry, theorem and definition. Then we're going to practice that a little bit. Let me see, we've got, I think that's it, yeah. So we will do more with this in class. So again, basic idea from today, from this part, is looking at the difference between what it means to be a midpoint theorem versus the definition, and angle bisector versus the definition. So again, I want you to go through these. You should be taking notes on this stuff. You can pause it if you need to, and then we'll do the actual we'll do the actual work when we get to class. Okay? All right. I will see you tomorrow. Make sure that you have these notes and have a wonderful evening.